Okay, now that we know everything we need to about duality, thanks to Lagrange and Karushkun and Tucker, we can get to the dual formulation of SVM, because the primal is not always easy to solve, and because of one additional bonus that we will get, which is although just one, but is quite powerful and worth working for. So, linear SVM, dual formulation. First, let's once again recall the primal. The primal formulation, we need to minimize the norm of the normal to the separating hyperplane, normal vector, subject to the following constraint, basically that everything is classified correctly. Now it can be recast as a dual formulation. Interestingly, the dual formulation is also a convex quadratic programming problem, QPA optimization, with now and variables, one per each data point. Let's recast it and then discuss it. So we can take the constraints, rewrite them in the Lagrange multiplier form, because it's an inequality constraint and we're minimizing. There is a negative sign here, and we go for each sample in the data set. Now it is an unconstrained optimization. We need to multiply the Lagrangian. Let's differentiate the Lagrangian and with respect to W and find the derivative. So as you see here, it's nothing but, so the square falls out and you just get W. And if you differentiate this part, you will surely get this, because only this part matters. And in this product, only X remains. So we equate the gradient of Lagrangian with respect to W to 0 and solve for W. Now we know that our W is this sum of this element-wise product of each sample times the label times the coefficient. Yeah, the Lagrange multipliers. So now, look, we have the W. Let's take it and plug it back in. Once we do that, the following expression falls out. It's still the same, but now there's no W anymore. To solve it, we need to minimize the following expression, and this is nothing but again a quadratic programming problem. Well, you see the square right here, but you'll see this much clearer in the matrix form, and yeah, it will become much clearer in the matrix form. So subject to positivity of Lagrange, or non-negativity rather, of Lagrange multipliers, and the sum of multipliers times y's labels equals to 0. Okay. So since, as we just established, RW is defined as follows, our final classifier after we do the training takes the following form. X is the new sample which you want to classify. You go through all of the samples and compute the value of this expression and take the sign of it. The beauty of the dual formulation of the support vector machine is that despite the large number of and here of the training points, this is not at all like the k nearest neighbor. It's a k nearest neighbor you would store all of the data as well. In the SVM and support vector machine, most of the constraints will be inactive. So basically, if you have your separating hyperplane and then class 1 and class 2 points here, the constraints -1 and 1, the constraint is inactive here. That is alpha I zeros and inactive here. The constraint is only active on the margin, and those points on the margin are called supports, and the number of supports is often sparse. It may not be sparse, it depends on many factors. Your problem, your choice of hyperparameters, we don't have any yet because we only are considering linear case, linear SVM, and so the only factor that determines in this case of the case of linear SVM that determines number of supports is your data. But usually it's very sparse, just a few supports, and that's what you store, just your supports. You store your, it's like with our eigenfaces in a sense. The whole data phase of faces was represented by these eigenvectors, the eigenfaces. But the eigenvectors were generated, they were synthetic, they were kind of putting together lots of features of all of the phases that went into the PCA process. In supports, we just select specific samples, only specific samples, and use only them for classification after the training, because after the training optimization, and we use specific QP solvers or some beautiful methods that we're not going to cover in this class, but you may look them up, such as sequential minimum optimization of John Platt, or Asuna's method of solving linear SVM, which are quite interesting and faster than off-the-shelf QP solvers. But the point here is that dual formulation of SVM gives us a sparse solution, and despite working in much larger dimension, remember primal works in the d-dimensional space, and the space doesn't depend on the number of features. On the number of samples in the training data set. D does not depend on the number of samples. Now, dual formulation is annoyingly dependent on the number of samples. So if you're working with big data, it becomes harder and harder to train support vector machine, because the larger the data, the complexity of the problem grows quadratically. Let me show you a different way to write the same form first. So we'll consider that in the next episode, in the next subsection, and it will become clear. So basically, linear SVM, we have now primal formulation and dual formulation. I will discuss some of the problems later as well that are easier in the matrix form, which I have on other slides in another episode. So the data may not be linearly separable. This is linear SVM. What do we do? Well, there are two solutions. One is map the data into higher dimensions and hope for the best with a feature mapping phi. Another solution is, well, just allow some error, introduce soft margin instead of hard margin, as we just considered. The support vector machine formulations that we just considered, both of them are called hard margin SVM. So by allowing some error, we will introduce a soft margin.